Let's just cut straight to the chase. Modern large language models, they are hitting a massive mathematical brick wall. Today, we're doing a deep dive into the SubQ architectural breakthrough. We're going to look closely at the hard data, the benchmarks, and the foundational math that is literally shifting the paradigm from those strict quadratic constraints to true linear scaling.
Okay, so the absolute bottleneck dictating the entire transformer era right now is this O of n squared reality. Because traditional attention mechanisms require computing the dot product of every single query with every single key, your compute cost just explodes exponentially as your context expands. It's a nightmare. But SubQ introduces a complete ground-up architectural shift to an O of n linear trajectory. And this fundamentally enables multi-million token contexts without the whole system just degrading or collapsing.
Here is our roadmap for this explainer. We'll start with the quadratic scaling bottleneck, move into the fully subquadratic architecture, break down the attention compute efficiency metrics, look at the RULR benchmark performance analysis, and finally, wrap up with MRCR version 2 and SWE-Bench.
All right, part 1, the quadratic scaling bottleneck.
So, standard transformers hit a really hard compute ceiling. As your sequence length gets longer, the computational power and the KV cache memory footprint of the attention layer, they just explode quadratically. It's a huge problem. And honestly, this is exactly why the entire industry has been forced to rely on retrieval augmented generation, or RAG, and these complex chunking heuristics. Processing massive contiguous corpuses of data all at once was just computationally impossible. Until now.
Which brings us to section 2. Fully subquadratic architecture.
Take a look at this. At a research scale of 12 million tokens, SubQ's ground-up redesign reduces attention compute by almost 1,000 times compared to standard frontier models. Yes, 1,000 times. By rebuilding a fully subquadratic architecture, where compute grows linearly instead of quadratically, the system completely sidesteps those catastrophic memory failures that usually plague standard models way before they even reach their stated context limits.
Moving right along to section 3, attention compute efficiency metrics.
Let's look at the actual numbers here. Comparing SubQ sparse attention directly against flash attention reveals a pretty staggering architectural advantage. As you can see, SubQ is 52 times faster, all while requiring 63% less compute. Let that sink in for a second. This totally proves that you don't have to sacrifice speed to drastically lower your compute footprint. It's a real game changer.
Let's check out section 4, ruler benchmark performance analysis.
Historically, right, if you built a subquadratic model, you had to sacrifice accuracy for that efficiency. But this trade-off, it's completely broken now. The SubQ1M preview model actually achieves a verified 95% on the RULR 128K benchmark. It even slightly edges out Claude Opus 4.6, which sits at 94.8%. So for reasoning over these really extended inputs, you are finally getting subquadratic efficiency right alongside true state-of-the-art accuracy.
And finally, section 5, MRCR version 2 and SWE-Bench.
Now, MRCR version 2 tests multi-hop retrieval and reasoning across massive context. It's basically a strict proxy for real-world enterprise workloads. The SubQ research build hits an impressive 83.0 on this. But what's more important is that the production SubQ1M preview scores 65.9. That literally doubles the performance of Claude Opus 4.7, which comes in at 32.2, and easily beats Gemini 3.1 Pro at 26.3.
And when we talk about raw coding execution on SWE-Bench verified, SubQ leads the pack again with a score of 81.8, pushing past both Opus 4.6 and DeepSeek 4.0 Pro. What does this actually mean for you? Well, it enables their SubQ code agent to load entire code bases into a single context window. Developers can now plan, execute, and review in one single pass, totally skipping that clunky coordination latency you usually get with multi-agent systems.
Okay, let's step back and look at the big picture here. At 50 million tokens, the whole design space for AI applications just shifts completely. We're talking about processing entire code bases in a single pass. You can ingest massive document collections and gigantic spreadsheets, or analyze unstructured database tables directly. Maintaining a continuous, persistent state over huge interaction histories just becomes the new standard. Those complex, fragile retrieval pipelines and agentic workflows, you don't need them anymore. The model just ingests the entirety of the data all at once. And look, none of this is just theoretical. The economic viability of these high-volume workloads is backed by a deeply rigorous research team. We're talking about 11 PhDs from places like Meta, Google, Oxford, and Cambridge, who spent years solely dedicated to solving the math behind this architecture from first principles. Add in $29 million in seed funding and leadership from Justin Dangle and Alex Whedon, and it's clear the infrastructure to support these massive workloads at scale is firmly in place.
So I'll leave you with this somewhat provocative thought based on the company's core thesis that efficiency is intelligence. If the architecture is no longer getting in the way, if that brutal quadratic scaling penalty is actually finally gone, what previously unbuildable hyperscale application are you going to deploy today? The constraint is broken. Honestly, it's time to build.